So I'm going to start very generally and then jump a little bit into evolution. And the basic premise of this will be that there's a different kind of universality than the one that physicists are familiar with, that we study all the time, but we don't call it that, but we probably should. So this is a simple plot. I sort of made it up, but you get what it is, which is over here is the number of parameters, free parameters in our models, and these are considered evils for reasons which aren't clear. But they're evil to Chopin, and they're evil to Arnold Newman, and they're evil to Newton, and for some reason human brains don't like to have too many free parameters. And here's some measure of approximation, or negative approximation, which is the granularity of the observation. And the thing that we've all cherished historically is this point here, which says the description of the world is, you know, a bit, but at the level of extraordinary precision. And that somehow has been what we've considered the gold standard of science. And this is the thing that got Eugene Wigner all hot under the collar in his very famous article on the unreasonable effectiveness of mathematics, in relation largely to the work of Dirac, but also of Mendel, which is often forgotten, which was, you know, how is it that the application of mathematics, which seems like a human deductive construct to a world, is so effective out of sample? And the reality, of course, is it's not. It's a lie, sorry. Most of reality is nothing like Wigner's reality. And most of reality, if we're honest, would be extraordinarily non-parsimonious to describe, and, you know, at the level of granularity that, say, was appealing to Wigner. Hence, the majority of disciplines are largely descriptive. And it's this tiny, tiny domain of existence, the inorganic, very simple world, that's actually been amenable to the kinds of unreasonable technologies that mathematics provides. So that's important to know, because really, I mean, I remember being invited to a conference on Wigner, and I just thought, I want to write the opposite paper, which is, you know, the reasonable ineffectiveness of mathematics in the natural sciences. And so, but there is this trick, and I've put this up in homage to Jeffrey, which is actually much of reality does something kind of interesting, that if you coarse grain it right, then all of a sudden it can become parsimonious. And what are these coarse grainings of the adaptive world? And there are many people in this room who've worked on it, and we don't really know. We don't quite understand what justifies that scale of analysis. Why the neuron, for example? How does the neuron emerge from the quantum field, right? Somehow, but it works. So you can write down Hodgkin-Huxley. You don't have to worry about more microscopic phenomena. So that's a very interesting fact, and I think if we could really understand this, we'd sort of solve the problem of complexity. We want to understand, again, Bob has this nice phrase, the hierarchy of things. If we understood what these things were, or these scales, that nature carves itself into or evolves into, it would justify parsimonious theory of the kind that the human brain seems to like. Now, I want to point out that if you coarse grain enough, then all of reality fits. And if you throw me out of a tower, Galileo has the answer, right? And so this is actually something kind of interesting, that when do we declare our theories to be successful, our parsimonious theories? Because I do conform to the laws of physics. And I do behave just like a point mass, you know, under an appropriate coarse graining. And I think that a lot of theory that I read actually is that kind of shit theory. It's actually coarse grained to such an extent that you're no longer explaining the thing that you purport to explain at all. And I think a lot of the history of complexity of science, to be honest, have felt like that. Because if you just reduce everything to the Ising model, then, of course, you've got it. You've solved the problem, and we're just ferromagnets, and we're all happy. So that's really important, and I think there's no theory that tells us where to draw that threshold. It's a question of judgment. When am I actually saying something interesting, as opposed to kind of averaging away everything I care about in order to be able to use mathematics? And I don't think we really understand that, and that might actually be a question of taste. Okay. So this is all obvious. Now, universality, the topic of this, goes beyond this remark to the fact that there are levels of coarse graining where the somewhat parsimonious theory applies to many different forms of matter, or many different species, or many different objects, and they conform to the same simple, compact description. And that's what we basically mean by universality, and that's very surprising. And there are two, and I think John alluded to this, there are two sort of schools here. One is it's an evolved, conserved property, and so its widespread features are just a function of genealogy. Or actually, there's something more interesting going on, which is convergence, which suggests that the adaptive system is reflecting some deep constraint in the physical world, and that's giving us universality, and Sam talked about this too. And that's difficult, and I'm not sure we have the answers to that. But I want to talk about another kind of universality, so now I'm labeling that axis complexity. So, and I put this up because it's fun. This is the even process, like a hidden Markov process. It's very simple. It's like a transducer. It spits out with a certain probability, a 1 or a 0. And if you were to observe that process, it's actually provably incompressible. If you were to sort of just keep looking at it and say, I'm going to tell me what the underlying pathway, the underlying process is, can I compress that sequence? You'd generate an infinitely large machine. But actually, it turns out to just be a rather simple two-state machine if you could deduce it or induce what the underlying generator of the stochastic process was. And there are many examples of this. And so we, in our world, make a distinction between the complexity of the object and the complexity of the process that generates it. And that was most fully realized, I think, by Charlie Bennett in his theory of logical depth, and then, of course, Murray Gell-Mann and Seth Lloyd in their theory of effective complexity, which turn out to be non-computable. And so they're sort of interesting theories which aren't very useful, but capture something very important. And it's going to be the essence of what I'm going to say, which is there are domains of science that want to compress the object, the regularity itself, and there are domains of inquiry that don't. They want to compress the process. And the object can be arbitrarily complicated. And in fact, essentially, from the point of view of inspection, seem to have no regularities. And I'm going to claim that's most of the natural world, actually. So you can call these constraints of matter, which is what physicists have historically been interested in, and those of us who do complexity as constraints of construction. And what are the fundamental processes of construction that can give arbitrarily complex or simple objects? So, the obvious ones, and again, I know that many people have discussed this. I'm not claiming Darwin is the only originator of such a concept, but it's perhaps the most famous, along with Adam Smith. Let me see. So these kinds of objects are, from the point of view of description, horribly complicated. They have lots of free parameters. If you want to make a distinction between a snake and a bird, you have no option but to look at the level of anatomy and its corresponding genetic encoding, or whatever epigenetic encoding. They're just not parsimonious objects. And now, they do have coarse-grained regularities, and Jeffrey will talk about scale. So there is a coarse graining where all of a sudden they just collapse onto a point. And they're objects of equivalent mass, but you've thrown out a huge amount of information by doing it. But that's marvelous, and that's one path. But there's another path. And they're in another class. They're in a complexity universality class, which is described by the same equations of motion. And these were first worked out in economics and biology. And so the most famous, which is Adam Smith with the invisible hand, and then Charles Darwin with natural selection. And they did something very, very different. Darwin was not able to explain, of course, why a fish was the way it was in all its particularities. He was able to explain a correlation. And so these people, interested in this kind of universality, are not interested in, if you like, the statistics and properties of the object, but the properties of correlations, and typically correlations between the object and the world. Within that framework, this axis is a measure of history. So the extent to which you deviate from physical parsimony is basically a history of broken symmetries. So you're just accumulating decisions which couldn't be predicted from the underlying physics. And so biology and evolutionary systems are complicated on that axis by virtue of having histories, and the length of the description is essentially a proxy for the length of their evolutionary history. So there have been efforts in this direction to derive these kinds of universality classes for that y-axis, and the most famous of which, and wrong, was R.A. Fisher's fundamental theory. So Fisher believed, as many of you know, that there was a theory as general as the second law of thermodynamics that could explain the origin of adaptive objects. And he wrote down this famous theorem, this thing, which is essentially there is this process which minimizes heritable variance, but we now know to be false. And he even knew it was false. And under conditions which I think, well, I won't go into, but essentially the obvious condition is game theoretic frequency dependence. Now, earlier than Adam Smith, the Reverend Bayes was interested in what hypothesis formation was. So he tried to formalize the idea of thought itself, and in a very famous paper that's worth looking at, this is how he wrote. It's kind of interesting. It's very Tractatus-like. It's actually quite difficult to read. But out of that came a very famous theory, which is Bayes' theorem, and this is how it works. You know, you have an observation. I want to know, say, between a choice of two, some sort of binomial process, what the probability measure is and what the weights are on outcomes. And I just perform a series of repeated experiments. And over the course of time, I come to a better and better understanding of the posterior distribution over states of the system. In this case, it's a fair coin. So the probability of landing heads or tails is a half. And over the year, maybe 5 or 6 of us have shown the equivalence of Bayes' theorem and Darwin's theorem structurally. They're actually mathematically identical in some limit. And you can actually then use natural language to do funny things, like talk about Bayesian Darwinism. Offspring are like the hypothesis of parents, formulated through the successive ancestors at predicting the current state of the world. And you can do Darwinian Bayesianism, successful hypotheses of the surviving ideas in the battle of existence in environmental experiments. So this is kind of interesting, that independently, two people thinking about very different levels discovered essentially the same mechanic, which we now know to be mathematically equivalent. But actually, you can go further. B.F. Skinner was studying reinforcement learning, and that can also be shown through some tricks to be of equivalent form. So the law of effect, Bayesian statistics, Darwinian natural selection, all conform to basically identical laws of motion, and they're all inferential dynamics. They don't tell you anything about the hypothesis that wins. They don't tell you anything about whether the organism has wings or fins. But they do tell you that when you observe the organism in its appropriate environment, there'll be a beautiful correlation. So this, and you can demonstrate that the thing that they're maximizing, actually prove that the Lyapunov function that these dynamics are maximizing is actually mutual information, that it's actually maximizing the correlation between the agent and the environment. So this is kind of interesting, right? There is a multi-scale substrate independent mechanism that has been discovered independently at least 3 times that explains the adaptive structure of matter at some level. This, I would claim, is universality, and I think much of what we do is look for this kind of law, not explain the particular structure of the object. But it begs really deep questions. All of these equations make very, very strong assumptions. It assumes that there is a consistent and clear feedback signal. It assumes that the system has near perfect memory. It assumes that you can encode, this is why mountains are not admissible, because the correlations that I'm talking about can't be achieved by mountain ranges. It assumes that the memory can encode states of the world to generate the correlations I'm describing. And it assumes that those together can produce this process of adaptation. These are assumed to be true. They're not derived. There's no theory which tells you how to create the memory. And some of us have been working on theories of individuality to try and derive from first principles this. So you can just map them. This pair, the memory encoding pair, we call these individuals. So interestingly, and I'm talking at lunch to Sam about this, if you go back and read Schrödinger, the entire book makes the assumption that these things exist. Right? He was very interested in memory and how the Habsburg jaw was preserved over many generations, but he never challenges or even addresses the question of where the individual comes from. And all of the mathematics that we have that have this nice universal property assume them. We don't derive them. So I think that I would be quite happy to call these protectorates or emergent things that enable the universal dynamics of inference that Bayes and Darwin and Skinner independently discovered. Now I want to go beyond nature and then I'll be done, which is this. Does anyone know what that is? That little equation, what it describes? There's no real reason beyond having read the paper. Well, actually, that is AlphaZero's learning rule. That's its loss function without all the regularizers. So that's it. Right? So if you read the paper, this is essentially the learning rule they used. But if you look at AlphaZero, it's a mess. Right? It's this very complicated, deep neural network. It was trained with 5,000 TPUs. We were trained too over many, many millions, if not billions of generations. The final object is opaque and a black box. And I've heard many people, my colleagues included, me included, criticize deep learning on the grounds that the objects are opaque, but so are we. We're totally opaque. Organisms are opaque. We don't understand our own processes at all. And so it would be completely mendacious and inconsistent of us, those of us studying complex systems, to accuse this community of using techniques that generate black boxes when we work with black boxes all the time. And the key affinity that we have with that community, and not with physics, is that we're both interested in the top line. We're interested in these processes which can give rise to these adaptive solutions, and not necessarily in trying to understand the logic of the engineered device in the end.
There's a paper just in Nature Physics yesterday on connections between physics and deep learning.
Well, there are. Of course, you can subject. I mean, people have done tons of statistical mechanics on the structure of, as we do. I'm making a little bit of a strong claim here, because I do feel that this community has been reviled by us, natural scientists, but not entirely justly, because anyone who invokes natural selection is basically playing the same game. So we have this I think the final slide, kind of interesting landscape that we're living in from the point of view of complexity. And there are two quite distinct approaches that share one common feature. So sometimes I call these the fine-grained paradigms of prediction. That's machine learning. Beautiful classifiers. They're just going to get better and better. There's no point denying that. And then this rival view, which consists in finding the right level of granularity at which you can be parsimonious. And scaling would be a beautiful example of that, or the Max-Ent theory in ecology would be a beautiful example of that. But you give away a lot. There's a lot that you simply can't address. But what they have in common is they both invoke processes that look like natural selection. So we actually share a great deal with the AI machine learning community because we're all interested in reinforcement learning-like things. It's just that in the end, I think we tend to favor a greater level of approximation in order to discover the natural scales and write down our beautiful parsimonious mathematics for those scales. But we have that in common, and in that respect, we're distinct from physics. And that's the common universality. I think that's it. Thank you very much. That's it. Yeah.
Thanks. That was an interesting talk. I wanted to ask about something that you brought up at the end and harkens back to some of the earlier discussions. When we talk about AI, the reason why some people don't like black boxes as the output of a learning process, even if the learning process itself has a very short description, is because even short descriptions can generate very complex things that are unpredictable. Yeah. And from an engineering perspective, of course, we want to be able to predict when things will work and when things won't work, right? And I think it seems like that's of course like an appealing property for physicists, if they can not only describe the universe in simple ways, but show that those simple descriptions have generalization ability, right? Yeah. Like certain invariance properties, right? So I wanted to get your opinion about what seems to me an important distinction between simple descriptions and invariance. Like, yeah, you could have one without the other, right?
Yeah, it's actually really interesting. Yeah. So you can ask, I do want to be pluralistic about this. I want to suggest that what the world wants is both, and finding these levels or macro states or whatever, protectorates or whatever language we use, is crucial actually for design and engineering. I don't disagree with that at all. I just wanted to point out this other form of very widespread universality that's also an equation, which is also very compact, which is extraordinarily substrate independent. And it seems to refer to something about the way information is extracted from the world. And that gets me to answer the second part of your question, which is the reason why I think this is possible, and you actually alluded to this, we discussed this at lunch, is that under this kind of infomax perspective, what you're really saying is the regularity you observe in the system is a reflection of the regularity of the universe and world. And it's really interesting that, in listening to Chuck's talks over the years, when he's looking at, compressed sensing, and in those cases, you're sort of finding the structure of the signal. But when you look at something like metabolism, what is that a reflection of in the world? Clearly, it obeys constraints. But those are harder. And when you look at the brain as a whole, what is that reflecting in the world? So I think that it's a whole open set of questions, I think, about what enables this. And I do think that's a big part of complexity science. I just wanted to emphasize the universality of inference, because it's not, for some reason, in the universality literature, it's not really talked about much. Jess and then Bob.
So I thought maybe we could have a little discussion about prediction, which I know came up earlier, or the other day with us. What here, so you mentioned universality with respect to maximizing mutual information with the environment. Is that, in what sense, so are you saying it's a universal feature of complex systems, the maximization? It's a kind of goal?
I would say it is, yes. Yeah.
Okay. So then, I mean, in physics, we have like quite precise predictions, but it seems like if we take that as a universal feature, maximization of mutual information with the environment, then the things that we can predict are design features.
Yeah.
And it's not about predicting like numerical values or it's predicting
mechanisms.
Predicting mechanism and structure. And I'm just wondering how one can make that. So that's, if I had more time, I would have ended my talk on this point too. Yeah. How one can make that feel more quantitative. Yeah. Or does one need to? So like when I say like I can predict, in order to maximize mutual information with the environment, I predict it has this set of mechanisms for maintaining robustness or whatever. How does one make that? Yeah.
Well, I'll give you the example, again, we and many other people have worked on, is the structure of error-correcting codes. So to the extent the robustness requires redundancy, we understand something about how you do error correction. And von Neumann kicked it off in a very simple way with averaging, but we have more sophisticated means of doing error correction. So I think that there are ways of making structural remarks on these designs which aren't just qualitative. It's not prediction to 20 decimal places, but it is saying there is a code and it has this form.
Well, it reminds me of like Juan Perez's paper I mentioned on showing that this one chemical reactor can recognize context-free grammars, context-sensitive grammars. So there, I mean, it's kind of like it's a thing it can do. it's not a prediction in the sort of physics sense, really. But there's a formal basis for it, a formal language for it. So that's the advantage of like Turing computation, is that it has this logical formal basis for it that allows us to determine when it's in play. So the question, I guess, is these mechanisms, would we require some sort of formal language to specify these mechanisms that would allow us to then say rigorously that if we observe this, it actually fits into this category?
Well, I mean, I don't know. There's a deeper question about what philosophers used to talk about a lot under the notion of the correspondence theory, which is scientists are getting extraordinarily shoddy about. So that is how you map your mathematics, applied mathematics, to data. And the good example that I think is extraordinarily weak is game theory. And so there's in economics, I'm going to pick on them, there's an extraordinary use of mathematical models, but the correspondence with reality is ridiculous. And I think it's partly because we don't think carefully about what that fit should be. And again, I think it's quite subjective. But it's a deep issue. I don't have a good answer to it. But Bob, do you have a last question?
Oh, I